Hello, and welcome back to the course on physics for engineers. So we are now on the second part of this chapter, which is all about the dynamics of rotational motion. So before we proceed with this lesson, let us review the previous topics. So in linear dynamics, so in the first part we discussed about linear angular kinematics. We'll now go to linear dynamics. So in your lesson on linear dynamics, you discuss about the cause of motion, which is the force. And you have encountered this very famous equation, which is called the Newton's second law of motion. This relates the cause of linear motion, which is force, and relates it to acceleration. So in a similar manner, we will be doing also this one. We will try to find the relationship between the cause of the rotation and its relationship to angular acceleration. So in this case, the torque is actually the reason for rotational motion. So the torque is the rotational analog for force. If force is the cause of linear motion, then torque is the cause of rotation. So the force is the measure of the tendency of a force to cause rotation. So you will notice from the definition that the torque is related to force. So it's the measure of the tendency to rotate, tendency of a force to cause a rotation. So the symbol for torque is given by this Greek letter tau, and it's the cross product of the radial vector or the radius vector crossed with the force vector. So if you have say a bolt and you want to rotate this bolt, so you use a wrench. So depending on where you want to act the force, the tendency of this bolt to rotate will depend on the force and the location, the radius, the distance from the location of the force, the point of action, to the axis of rotation. So the magnitude of this is actually RF sine theta. Magnitude of the first vector, magnitude of the second vector, sine of the angle between them. So of course, the maximum value of torque happens when theta is equal to 90 degrees. So when sine is 90 degrees, then that is the maximum value of sine theta is 1. And sine theta is equal to 1 happens when theta is equal to 90 degrees. So R here is the radial distance from the axis of rotation to the point where the force is acting, the point of action. And theta again is the angle between the radius vector and the force vector. So in this specific example, the angle between the radius and the force is 90 degrees. So you will notice that the tendency to rotate there is directly proportional to the radial distance and the force. The greater the force, the greater the torque, the greater the tendency to rotate. The larger the radial distance, then the larger the torque, the larger the tendency to rotate. So torque, obviously, since this is a cross product, they obey the right hand rule. Okay, so R cross F equals torque, the tau. So if this is your R and this is your F, so if you act a force in this direction, then the tendency to rotate is in this direction. So if your fingers curling around your thumb is the direction of rotation, then the direction of your thumb is the direction of the torque. So if this is the rotation, then this is the direction of the torque. Your thumb finger. So since our board is only two-dimensional, we will define positive and negative torque. So if you have a torque that's out of the page, such as this one, it's going towards you. So meaning it's counterclockwise rotation, that is a positive torque. If you have a torque that is into the page, so again, this is a vector. You are seeing the bottom of the vector. You are seeing the tip of the vector here, the torque vector. So the vector is into the page. So in that case, the rotation is counter clockwise. And in that case, the torque is negative. So that will be our convention. So that will be our convention for torque. Positive torque out of the page, negative torque into the page, or clockwise rotation. So from Newton's law of motion, torque and angular acceleration also have their relationship. And actually, it's very similar to Newton's second law. So this is the rotational analog of Newton's second law of motion. So the torque takes the role of force. The angular acceleration alpha takes the role of acceleration A. And the role of mass is taken by this quantity I called the moment of inertia. So please don't, in physics, there are many quantities or variables which are repeating. So later I will repeat as another different variable or another different physical quantity. But as of now, as of this chapter, I is what we call the moment of inertia. So the moment of inertia is the rotational version of mass. So this is basically F is equal to M times A. So F is the role of F, the role of force is assumed by the torque. The role of the mass is assumed by the moment of inertia. And the role of acceleration A is assumed by the angular acceleration alpha. So moment of inertia is the measure of difficulty to rotate. If you have a large moment of inertia, then that object is hard to rotate. If you have a small moment of inertia, then that object is easy to rotate. So it's actually just the summation of mr squared. The number, the mass in kilograms, and the radius or the radial distance r from the axis of rotation. So you add all the mr squared to get the moment of inertia. So example here, you have two masses, say m1 and m2, and basically they're just the same. Now, if the radius r, distance from the rotation axis, is very small, so if r is very small, then I is also small. You have a small moment of inertia. In that case, it's just easy to rotate this object, or in this case, this apparatus. Now, if you move the masses farther from the rotation axis, meaning there are values now, the radial distance is now very large, or it's now large. So a large radial distance means a large moment of inertia. In that case, a greater moment of inertia means it's hard to rotate that apparatus. So for solid or continuous objects, these are the different moment of inertias. So if you have a slender rod, such as this one, a pen, then its moment of inertia is 1/12 the mass m times the length squared, if the rod is rotated about the center. Now, it's a different case if the rod is rotated around the edges. Its moment of inertia becomes 1/3 ml squared. From 1/12, it becomes 1/3. So 1/3 is greater than 1/12, which means it is harder to rotate a slender rod at the edges, at any of the edges, as compared to rotating it at the center. It's easier to rotate a rod at the center as compared to the edges of the rod. So here is for a rectangular plate to the center, a thin rectangular plate along one edge, say a door, rotating door. You open a door, so the scenario is something like this. You are rotating with respect to the edge of the door, where the hinges of the door are located. Now, how about if you have cylinder? So if you have a hollow cylinder with inner radius r and outer radius R2, R1 and R2, you get that moment of inertia. If you have a solid cylinder, it's just 1/2 mr squared. If you have a thin-walled hollow cylinder, very thin, such as a tin can, you will have mr squared. Now, just comparing these two, 1/2 mr squared and mr squared, meaning the thin-walled hollow cylinder has a greater moment of inertia compared to a solid cylinder with the same mass, assuming they have the same mass m. So that means it's easier to rotate a solid cylinder with the same mass as a thin-walled cylinder because the thin-walled hollow cylinder has a larger moment of inertia. That one. It's easier to rotate solid cylinder. The same is also true for spheres. A solid sphere has a moment of inertia of 2/5 mr squared. A thin-walled hollow sphere has a moment of inertia of 2/3. So 2/5 is less than 2/3. So smaller moment of inertia means it's easier to rotate. It's easier to rotate a solid sphere as compared to a hollow sphere. So let's now have an example. Okay, basic example. Why do you think doors are designed in such a way that the knobs are as far as possible from the hinges? So if this is your door, the axis of rotation is actually this edge of the door. And this axis of rotation is where the hinges are located. Now, if you will notice, the doorknobs are on the other side or on the other edge of the door. Why do you think is that? Why do you think there are no doorknobs that are at the center of the door? So it takes into account the torque. Say maximum torque. The maximum torque is Rf. Sine theta is equal to 1. So you get a maximum torque, a larger tendency to rotate if your R is also large. So this is actually R. This is just your R, a small R, then that will correspond to a small torque. But if your R is as large away as possible, so this is already the largest R possible for a door. Because you cannot put the door beyond the door. You cannot put the doorknob beyond the door. That's already the edge of the door. So you put your doorknob as far away as from the axis of rotation as possible. And that is the other edge of the door. And that will give you the largest R, and that will give you also the largest torque, meaning the largest tendency to rotate. So the tendency to rotate, if you put the doorknob at the middle, if you exert the same force, will just be half as compared to a doorknob placed at the edge of the or at the edge of the door. That one. So it obeys the torque principle. So second example. So this is now a example for torque calculation. So a weekend plumber, unable to lose a pipe fitting, slips a piece of scrap pipe called a cheater over his wrench handle. So this is usually done by carpenters and plumbers. So they use a pipe, a hollow pipe, and they insert the edge of the wrench on the pipe so that the arm now, the length of the arm of the wrench is extended. So basically it's an extender. And the purpose of that is to increase the radial distance R. So it's called a cheater. They're basically cheating. They are not actually cheating. They're just basically using the concept of torque. So you need your radius arm as long as possible. And then he applies his full weight. His full weight is 900 newtons. So that's already his mass times G, acceleration due to gravity. To the center, to the end of the cheater by standing on it. So he stood at the end of the cheater where the weight acts is 0.80 meter. So the wrench and the handle makes an angle of 90 degrees. So this is the picture. Find the magnitude and direction of the torque. He applies about the center of the pipe fitting. Okay, the direction of the torque is easily obtained. So the tendency to rotate here is in this direction. So the rotation is this one, counterclockwise. Therefore, our torque will be, in this case, the torque at this point. So the torque is actually at this point at the axis of rotation. The torque at this point is out of the page. So we already know the direction. So to solve for the magnitude, so the magnitude is just easy to solve. Torque is R, radial arm distance, F sine theta, where theta is the angle between the R vector and the force vector. So this is the R vector from the axis of rotation towards the point of action. That is our R. And that is our F. Now, if we draw an XY coordinate system, our force, or sorry, our R, our radius vector is actually in quadrant number 2. This is our R. It's in quadrant number 2. Our force is downwards, which means it is in, it's not in any quadrant, but it's in the negative y-axis. This is our force. And theta is the angle, this angle here, between the two vectors. That is your theta. This is actually the common mistakes of students. They always use the given angle. 19 degrees is actually just this small angle here. So from the figure, this is 19 degrees. But that is not the angle between the radius vector and the force. The angle is actually 19 degrees plus this angle here, which is 90 degrees. So theta here is actually 109 degrees. So theta is 109 degrees. And using those values, R is 0.8, the force is 900 Newton, sine of 109 degrees. The final unit is Newton meter. There's no special unit for torque, it's just force times distance, Newton meter. And you will get a value of 680.8 Newton meter. The direction of this torque is out of the page, signifying a counterclockwise rotation. So out of the page, so towards you. Out, this is the direction of rotation. This is the direction of the torque. It's towards you. That one. So the only crucial thing in calculating torque is the angle between the radius vector and the force vector. Even though at times you will get the same result, but even though because there are two angles with the same sine theta, so even if you obtain the correct result but you use the wrong angle, that is still a wrong solution. Okay, so moving on to another example. Okay, this is an example of the relationship between torque and angular acceleration. Okay, you have a cable, it's wind or wound, cable winding, you know. So wound or wind around a solid cylinder of mass 50 kilograms and diameter of 0.120 meters. You have a solid cylinder here. So you wind it in a solid cylinder. So you then pull the cable. So after you wind the cable in the cylinder, you wind it how many times? You then pull the cable with a force of 9 Newton, and this caused the cylinder to rotate without slipping. So we will assume that the cable and the cylinder basically rotate together. So what is now the acceleration of this winding cable? So we are asked to find the acceleration A, the linear acceleration of this winding cable. So this is basically tangential acceleration. You are asked to find the tangential acceleration. So in this case, the acceleration of the cable is the same as the tangential acceleration at the tip of the, or the edge of the cylinder. So the acceleration of the cable is just the tangential acceleration of the solid cylinder. Okay, so in this case, your acceleration is just r times alpha. Your r here is just given the diameter is d over 2. So the diameter is 0.12, so you will have 0.06 meter as your radius r. So we then use the rotational analog of Newton's law, the non-vector form. So summation of torque is just I alpha. Now, okay. So if you will notice, there are three forces acting on the cylinder. The force that you use to pull, 9 newtons, and then there's the normal force, and then there's the weight. But take note, these two forces, the normal force and the weight, acts on or at the center of the cylinder at r is equal to 0, meaning they have no contribution to the torque, because the formula for torque is r f sine theta. So r is equal to 0 at the center. They're acting at the center of the cylinder, or at the axis of rotation, so they don't have a contribution to the torque. So the only contribution to the torque in this case, in this summation of torque, is this f here. Now, this is r, the r vector, and that is your f. The angle is 90 degrees. So therefore, rf sine theta sines of 90 degrees is 1. So the total torque is just r times f. This is I times alpha. Now, if you will recall, for a solid cylinder, the moment of inertia for a solid cylinder is actually 1/2 the mass times the radius squared. That's actually the moment of inertia of a solid cylinder, alpha. Okay, so from here on, we can now solve for alpha. Divide both sides by r. Divide both sides by 1/2 mr squared, and you will get what? So you'll have 2f over mr. So this is now the angular acceleration. So to solve for the acceleration, A is just r times alpha, where alpha is, so acceleration is r times alpha, so alpha is 2f over mr. So acceleration is just 2f over m. So you only need two values in order to solve for the acceleration. So it's just the force over the mass. So in that case, you have the force is 9 newtons, the mass is 50 kilograms. So the acceleration, the final unit of this is meters per second squared. So your acceleration will be equal to 0.36 meters per second squared. So this is the tangential acceleration at the edge, at the points at the tangent to the cylinder. And that is also the acceleration of your cable, because we assume that the cable or the cylinder rotates without slipping from the cable. So that one, easy peasy. Okay. Do we have another example? Okay, that is the last example. So in this chapter, we basically have a rotational version of Newton's second law of motion. So torque is the rotational analog of force. So for our last last lesson of the chapter, we will be discussing about momentum. So the rotational version of that is angular momentum, and we will try to, similar with linear motion, wherein we relate the impulse or the change in linear momentum with the net force. We'll also do that for angular momentum. So I will see you again in the next lesson.